Welcome to this presentation. We're looking at the analysis of 1D problems. We talked about 1D elements in the previous presentation. So here we're going to look at using those to analyze some different problems. And specifically, we're going to look at a heat transfer problem as well as a fluid problem, and more universally how you can apply it to other problems, but focusing on these two for now. We'll also have an ANSYS example in the middle of this. All right, so you can go to lecture materials. The link again is down below in the notes. For folders and the notes, you can go to, again, the link. And we're looking for the analysis of 1D problems. All right, so where are we headed in this presentation? We're going to analyze the one-dimensional problems, as I mentioned, in heat transfer as well as fluid mechanics. And we're going to do some ANSYS work as well. And that'll be specifically with a heat transfer problem. All right, so heat transfer with one-dimensional linear elements. So we've looked at a fin briefly before. We're going to look at it more in depth here. But we have a heat source at the base over here. And modes of heat transfer, we have conduction in the x direction. So conduction along the fin this way, moving from hot to cold. And we have convection to the surrounding fluid to the fin surfaces. So we got convection that's going across the surface here, as well as on the back side there. So the governing differential equation that we have for this is this. So we got conduction that's happening here, and we have the overall convection that's happening between the temperature on our fin and the temperature of the fluid that surrounds it. So K is our thermal conductivity. A is the cross-sectional area in the direction of conduction. All right, so it's going down the cross-sectional area as you move down the fin. H is the convective heat transfer coefficient, and P is the fin perimeter. So that accounts for the heat loss from the surfaces of the fin. And TF is the temperature of the surrounding fluid. And TB is the temperature of the base, which is the source, not shown in this equation, but will come up as we go through this. All right, so we're using linear elements, so we need two boundary conditions. One boundary condition is pretty obvious at the base, at x equals 0 is the temperature at the base. For the second boundary condition, we could have one of the following. So one, we could just say, hey, we know the temperature of the fluid at the tip of the fin, and that's going to be constant. It's going to be constant at the fluid temperature. So it's so long that there's not going to be any additional temperature increase at the tip of the fin. We'd also have no heat loss at the tip. So you can see the conduction, basically the temperature gradient dt over dx is equal to 0 because K is not going to be 0 and area is not going to be equal to 0. So the temperature gradient at the end of the fin is not going to exist. There's not going to be a gradient, so basically it'd be insulation at the tip. Third option is we could have heat convection to the fluid at the tip. So here we have our conduction equation. So we could have conduction to that last element, and then we have convection from that element to the fluid that surrounds it. So we'll look at these here as we move through. The governing differential equation represents an energy balance of the fin. All right, so we will approximate the solution with linear elements of the form using our linear shape functions. So the shape function node I and shape function node j multiplied by the temperatures at those corresponding nodes. So there are shape functions in global coordinates, as well as in matrix form there. All right, so hopefully you have that. Again, if you need to go back and check out the 1D elements presentation. All right, so the general form of our differential equation, as we mentioned before, is this. We can also represent it as this. So if we take our K and our A and we generalize to just saying, hey, there's a constant there, a coefficient, as well as with HP, we have a coefficient, so the negative sign would be wrapped up in the coefficient here as well. And then we have just a constant there, coefficient 3. So there's our A minus HP, and convection coefficient times the perimeter times the temperature of the fluid. All right, so let's go one step further. Let's go even further, and let's make our differential equation very general and applicable to other problems. So we're going to set the temperature equal to psi. All right. And we need to solve this thing using, all right, drum roll please, we've got Galerkin formulation. All right, so one of these weighted residual methods that we learned earlier, so you can go back and check that out. It's the weighted residual presentation where we talked about the Galerkin formulation. So we're going to use that now as we go through this. All right. So remember, the basic idea of what we're doing is we want to assume an approximate solution first. So what do we think the solution is going to look like? And we're going to substitute that in to the governing differential equation, right, and then solve it. So the result has some residual error. Then we work to put that to 0. Right? So the Galerkin formulation, we're going to multiply the residual by a weighting function, average it, and set it equal to 0. Right? So here's the governing differential equation that we're going to have, that we do already have, actually. Here's the weighted residual function. It's going to have the form of the assumed solution, and then we're going to integrate across the domain, across our dx, and that's going to be our residual, and we're going to set that equal to 0. Right? So the weighting function must be the same form as the approximate solution. So again, we're going to use the linear shape function as our to plug in there. So we're going to got 3 nodes in a row with elements in between. So nodes I, j, and k, the element e and element e plus 1. So the residual equation for node j, right, for node j here becomes the residual node j from element e and plus the residual that we get from element e plus 1. So they both contribute to what we see there at letter j. All right, so combining those, here is our shape function at node j, right, for the element e. And here's the shape function for node j at element e plus 1. Here's our governing differential equation. All right, and so we're going to go from I to j and integrate from dx from I to j, and then dx from j to k. All right, and we get those 2 forms of our equations there. All right. We will have a residual equation for each node in the finite element model. For example, here if we have 5 nodes and 4 elements, we'll have a residual for each node where R2 is the residual for node 2 from element 1, and we have to get the residual for node 2 from element 2. So there's residuals for a node from the element on either side of that node. That's what we have to combine here to make sure we have the full accounting of the residual at a particular node. All right, so let's examine the nodal residual equations for nodes 1, 2, 3, and 4 here, specific to this problem. So again, we look at the residual for node 1. We have the shape function at node 1 for element 1, the governing differential equation, and we're going to integrate that over from nodes 1 to nodes 2, set that equal to 0. All right, so that's all for element 1. So for the residual at node 2, we have to get the residual of node 2 from element 1, and we need to get the residual for node 2 at element 2. So now we're going to have more here, right? Because element 1 only had one element next to it. There was only element 1. There wasn't element on the other side of it. So here we got what's happening at element in element 1. So the shape function for node 2 in element 1, in the governing differential equation, and we have the shape function for node 2 in element 2, and the shape function or the governing differential equation there. All right, so the arrows point out here element 1's contribution over here, and element 2's contribution over here. We do the same thing for node 3, so we got element 2's contribution here on the left, and we have element 3's contribution here on the right. Set that all equal to 0. And for the residual at node 4, again the contribution here from element 3, and the contribution here for from element 4. All right, and you continue that on and on and on the rest of the way. So in general, for element E with nodes I and J, the residual at node I for a given element is the shape function of that node in that element times the governing differential equation. All right, and the residual for node J in that element is the shape function of node J in an element times the governing differential equation integrated over the distance from J to K. All right, so that's our two different residual equations. So now let's manipulate the second order term from the governing equation into a first order term. Just have a correction I want to make here. Realized that again, this is all for element E, and element E consists of node I and node J. So that should be just like it is up here. The location of node I integrated to the location of node J. This should be I. It's a strange looking I to J. So just heads up with that. I think I had J and K there, and I get mixed up there. So this is I and J. All right, so again, let's go back. We're going to try to get this second order term into a first order term, and we'll see why here in a bit. All right, so keep your finger here or in the notes, or just come back to this note the time, and because we'll come back to this point. All right, so if we take the derivative of the shape function times the derivative of psi with respect to x, and then using the chain rule, right, so here's the derivative of shape function node I times the derivative of psi with respect to x. We get the, here's that second derivative times the shape function node I plus what to the term we see here. All right. So if we rearrange this algebraically, right, because we want to isolate this and then substitute for it. So we're isolating this the second order derivative and getting the other terms by themselves here. Okay, so we're going to substitute equation 3, that was the one at the bottom of the previous slide, into equation 1. So equation 1 was the one for the residual at node I. And solve, and knowing that we got the shape function at node I, and we have this expanded here form for finding psi at any location in our element. Right, so the residual at node I becomes, here's our first term. All right, so we've expanded our second order derivative into these two terms. Here's our first order term for psi, and then here's the coefficient of 3. All right, so here what we've done is we've gone through with the integration of this first term. Right? So going through that integration of the first term creates these two terms. The second term has been expanded, so we've substituted for psi right here, and that's where we get everything here that's in parentheses. So we did the substitution of psi, which is up here at the top. And then for the shape function in node I, that's what's right here. So that's the shape function in node I was substituted in there. And then the last two terms here, or three terms, the first two are from the integration of the first order psi term, and then the last term there is the integration of our coefficient of 3. All right. So we're going to make a substitution here, and so you can go back and forth if you need to. So we know the shape function at node I is 1 at node I, and shape function for node I is 0 at node J. So knowing those two, we can plug in and we can solve this one further. So we get the psi at node I and psi minus psi at node J for that function there. And then these guys are pretty much what they were on the previous slide. We can do the same thing. So equation 3 was the second order, expand second order into first order derivatives. And equation 2 was the one for the residual at node J. So we get basically the very, very similar form. So here's residual at node I up here, and residual at node J down here. And we're going to take those and we're going to put those in a matrix form. Right? So remember, psi is the temperature, or can be the temperature for our problem. Right? So we're going to symbol this into matrix form. So here are the two residuals here. Right? Here's the first part of that second order derivative. Here's the second part of that second order derivative. This is that first order term, and then here's the last term there, the third coefficient. All right, so setting the residual equations to 0, right? So if we set these two guys equal to 0, we can isolate this guy, this last term by itself, equal to all the rest of the terms. All right, so again, that's a lot, but again, we're gonna go back and get more sense of what's happening. But I wanted to see it from a general term, and then we'll go back to it. So notice the overall form here, though. I'm gonna just go back real quick one slide. So notice what we got here. This looks kind of familiar, right? This equation. All right, so we have these two, which looks like stiffness matrices. All right, What do we got over here? Contributes to the element conductance and load based on the boundary conditions. All right, so that's the second order term, so that makes sense. Contributes to the conductance. All right, this is the element conductance, or you can think of it as a stiffness, right? The stiffness matrix. This is also an element conductance, but in this particular problem, it's convection for our problem. It's a convection term. And finally, we have a thermal loading. So for while we had a load matrix due to force in our structural analysis, in our thermal analysis is a thermal load. All right, so looking at that first term, all right, what we've done here is we've substituted in, let me go back here. All right, we've substituted back in for C1, substituted in our Ka, so for our first term there. All right, so for our stiffness term, all right, so our first stiffness term for C1, we're substituting back in Ka, and just as we did up here. And this is the conduction along the fin. All right, so conduction coefficient times area over length, and then we have these stiffness values in here. So it concerns the conduction along the fin. This next term, we're substituting back in for C2, our H times the perimeter. Right, this is the convection loss from the surfaces of the fin. So if we're going down the fin, and fins like this, we're going this way, right? This second matrix up here refers to the convection along the surface as we move along it, whereas this one refers to this conduction along the fin. All right. And this last one is the convection load from the fluid. All right, so let's look at this. So the third boundary condition, all right, from slide 6, we talked about the 3 different options we had for the boundary condition at the tip. The third one was we had a convection from the tip. So this is the temperature at the end of our fin. So therefore, if we put the equation together here, we have conduction that would happen into the tip, we would have convection from the tip, and we'd have these other terms. All right. So basically what we're doing here is we're looking at, if we had an element here, we have node I and node J, and if J was at the tip, it would be the one that's interfacing, having the convection at the tip. So that's why there's no terms here. This equals 0 at node I, and then we have convection here for all the J terms. All right. So there's the boundary condition, all right, boundary condition for the convection matrix, and then a force function because of the temperature in the fluid. All right, so both those only apply to the last element at the tip because that's where that shows up. We have the convection from the tip. All right, so let's combine the whole thing together. We got our stiffness, we got our temperatures, and we got our forcing functions. All right, so only for the tip element, right, we combine all 3 of these things where we have our first stiffness matrix, right, our second and our third boundary condition matrix. All right, so in that case, our total element stiffness contribution is 1 from conductance, 1 from convection to the side, and 1 from convection from the tip. So on all the other elements, we exclude this one, but except for the tip. Right? So exclude from the last element if no heat loss from the tip. So if we don't assume convection at the tip, then we exclude this. So again, we'll get practice with this. I'll show you how this works. All right, for the forcing function, again, you want to include the C3 term that we already had, and then we also have boundary condition. All right, so we can exclude this one as well if we don't have convection from the tip. All right, so okay. Hopefully this all looks familiar. All right, so we're going to, again, from kind of the stiffness perspective, now we're going to assemble a global stiffness matrix and load the matrix for the whole finite element model. All right, so solve the same way as we did with the mechanics solution. So you just need to put all those things together here. All right, so you can find more examples in textbooks and online to give you other experiences with that. All right, so to find heat loss, so if we have all those things, we want to find heat loss. So I'll show you here with Q. I also see heat transfer, and in heat transfer I use Q dot, so rate, heat transfer rate. So due to convection on the surfaces, basically we need to sum the Q dot that happens through all the surfaces. So here's our convection Q dot equation. So HP, we don't have area here because we're going to integrate along the x direction, so it's just the perimeter. And then we have the temperature of our surface minus the temperature of the fluid. All right, so substituting in for the temperature equation, that's what's coming in here. So substituting in here the shape function form of our temperature. Right, substitute in there. And so we're going to substitute now in for the shape functions, and you can integrate those with respect to x, and you come up with this form of our equation to determine the total heat loss from a one element. All right, so not the whole fin, but just particular one element. All right. So again, H is the convective heat transfer coefficient, P is the fin perimeter, and L is the element length. So now we're going to work on a conductance problem. And we're going to have convection at one end. What we're going to look at through is conduction through a plane wall. And this wall basically works infinitely in these directions. And we're just going to have convection here to the fluid. So node 5 here interacts with that fluid. Again, 4 elements, 5 nodes, and we're going to develop our matrix here. All right, so here's the general form of the stiffness matrix for a thermal case. So we have, again, the conduction, we have convection from the outer surfaces, maybe say at least in the fin case, it was the horizontal surfaces, and then this would be the convection at the tip. All right, so in this case, we're in a plane wall, so we don't have any convection at all, so we don't have to worry about either of those terms for the first 3 elements. So there's element 1, 2, and 3. So those don't have any convection at all. At element 4, we do have convection. Right, so we do have to include convection, and it's convection from essentially the tip of the wall. So we just have the tip convection term, and that's only at node J, so that we have zeros for the 2 node I's in element 4. All right. So again, all those cases we're going to assume the area is 1. For the forcing function, again, we have convection from the surfaces, so the perimeter of our wall, but it's an infinite wall, so we're going to ignore this term. And we also have convection from the tip, but we have the tip in one case. So for the first 3 elements, those are all 0. But for the 4th element, we're going to include just the tip, right? Because we have the outer surface of the wall that interacts with the fluid. All right. So we're going to assemble our global stiffness matrix. So again, here's where we're going to put all of our stiffness matrices together. Globally, we have all our temperatures here, and our boundary conditions say we got temperature at the surface going to be defined at node 1. All right, so it's going to be defined there, and then at node 5, we have this boundary condition where we have the HA times TF. So we have the convection boundary condition that's driving the heat transfer out of the wall. All right, so that's how to set it up, and then hopefully you can run it the rest of the way. So now we're going to look at a specific ANSYS example where we can apply and use our thermal elements. All right, so a brief setup for that. We have link 31, which models radiation heat transfer between 2 points in space. We have link 33. Some books use link 32. We're going to focus on link 33. Models transfer of heat between 2 nodes via conduction. And we have link 34, models transfer of heat between its 2 nodes via convection. All right, so we're going to focus on 33 and 34 in this example here. So here's an example. We've got a wall of different materials, different K values. So we got 0.08, 0.074, and 0.72 for looks like some brick. And actually, I believe this is a representation of a chimney or of a furnace. So we have inner surface temperature of 200 degrees C, very hot inside. Again, some refractory materials to help insulate things. And then we have the outside fluid, outside air at 3 degrees C, and a convection, constant convection of 40 watts per meter squared K. So we're going to break this up fairly simply. We're going to have 3 elements, 4 nodes. So 1 element for each of our materials. And let's do this. All right, so I got ANSYS up and running already. And just start it up. And so I'll go in and I'm going to create a title. Change title. And we'll do heat transfer problem. I like to go into preferences and just help myself out. I'm going to just look at the thermal items in the menus. So select that and click OK. We'll just work our way down here. We'll do element type, add, edit, delete. I'm going to add, and I'm going to do a thermal mass, and specifically a link. So that's the one we looked at. So we have the conduction link, link 33. So go ahead and hit apply on that. All right, and then we'll do convection, and we'll hit apply on that, and OK. So, I get twice there. Oh, I hit OK. You need to hit. I should hit cancel. All right, so we'll delete that one and hit close. So we got one conduction link and one convection link. So close that. Go into real constants, and we'll add, edit, delete, and add. We'll start with the conduction. Click OK, and just put an area of 1, and hit apply here. Really, that should be all we need to do. And we need to do one for convection. But what we found in the past is that it needs each different. If you're going to have different conduction coefficients, you should have a different real constant for each conduction coefficient. So we're going to create 4 total real constants, and then 3 different conduction coefficients and 1 material for convection. So we'll see that here, but again, we should do 4 of these. So we'll do number 2 here. Again, area 1, apply. We'll do 3 and area 1. That's good. We'll click OK on that one. Then we're going to add one more because we need one for convection. So make sure you're on type 2, convection. Click OK. Change the area to 1. And click OK. Now we have our 4 real constants. 3 for conduction and 1 for convection. Click OK on that. All right, so we'll go to material properties and material models. And this is a new one for us. We go into thermal, conductivity, isotropic, and we'll just work our way across again for the different conduction coefficients for a model. So 0.08, and we're locking it in with the units. Again, so watts per meter K. So 0.08, and we'll click OK. And we'll go to material, do new model, make sure number 2, click OK. And we'll go isotropic again, and we got 0.08 was the first one, 0.074, click OK. Material, new model, OK for number 3, isotropic, and we got 0.72, click OK. All right. And one more time, material, new model, and we'll go OK with 4. We're going to come down here and make sure you get the convection or film coefficient. And for convection, it's 40 watts per meter squared K. Click OK. Looks good. We'll close out of that and get back to our ANSYS. And save DB. Make sure you get that. All right, so let's set up our working plane so we can get our nodes figured out here. So we're going to work plane settings, go grid and triad. 0.05 is fine. Again, just look back at the dimensions here. So yeah, 0.05 for 5 centimeters. We need 15 and 10, so that's 25 and 5 is 30 centimeters. So come down here, spacing, get that to 0.5, minimum 0. Maximum, since we're going for 30 centimeters, is 0.3. And go ahead and click OK. Okay, get back to ANSYS here. Okay, work plane. Let's display the working plane now. And get a panned over there. All right, looks good. So we're just going to be working right here. It's just a 1D analysis, so we're just going to be right on this line right here. I don't really worry about the rest of the 2D aspects of it. All right, so we're going to do modeling, create nodes on working plane. So node 1 we're going to have right there. Node 2 is 5 centimeters over. Node 3 is going to be 15 centimeters over from node 2, so right here. And node 4, we're going to go 10 centimeters over from there. And now node 5 is the node we're going to have for declare the temperature of the fluid. And then we're going to have a convection element between node 4 and node 5. So we're going to put 5 right where 4 is at. So we'll put it right on top. It looks like it disappears. And we'll click OK. And it's hard to see what's going on there. So always go into list. You can go to list, check out nodes, and look at coordinates and angles. OK. So we see we're at 0 for node 1, and then 0.05 for node 2, 0.2, 0.3, and a 0.3 again at node 5. All right, so we're going to exploit that to put in our convection stuff. All right, so let's make sure our numbering's on. And turn on that as well as our elements, that we don't have any elements yet. All right, it's got the numbering on. We can turn off our working plane so we can see what's going on. Let's save DB. All right, so let's do our elements now. So create elements, auto-numbered through nodes. And we'll go ahead and click on nodes 1, then 2, middle click, and click OK, because we only want to do one element because we need to make sure we move on to the next one. So hopefully we got the right one, that one. All right, so it's link 33, that's a conduction element, and material 1 and real constant 1. So now that one's good. So then let's go to element 2, and we want element 2 to be material 2. So we get that conduction coefficient, and just for getting things to work properly, we'll do real constant 2. So click OK, and auto number through nodes, and go 2 to 3, and middle click, and OK. Go to element attributes, we'll go up to material 3, real constant 3, and OK, and auto number through nodes, and go from 3 to, oh, what happened there? So there's 2 nodes right there, so we get to pick. So we want to pick node 4, or we could pick node 5, but we want 4. So click OK, and OK, and then we get element 3 that shows up there. And now we want the convection element, so let's go to link 34, and we'll do material number 4 and real constant number 4. Click OK, and auto number through nodes, and we'll click on those 2. So 4, we'll do 4, and I'll come back and I'll pick 5. I got 5, click OK, and OK. So again, I want to check this, make sure I'm right, so I'll go to list, elements, and nodes, attributes, and real constants. So I got element 1 is material 1, type 1, and here's real constant, so 1, 1. And element 2 is 2, 2. Element 3 is 3, 3. Element 4 is 4, 4. Right, type 2. And we see the nodes 1, 2, 2, 3, 3, 4, and 4, 5. So that looks like what we want to have there. Again, if you need to go back and troubleshoot some stuff instead of create, you might need to move or modify. So I could have done all these elements with just the conduction element, and then come in here and modify some of the attributes of one of those. So I can just show you right here. If I click on one, all right, attribute to change, I could change material type, element type, real constant, so I'd have to do that a couple times for the ones that were off. All right, but I can come back and do that. You can also, if you need to, just delete the element outright if you need to. All right, so we got our elements nodes defined. Now we're ready for boundary conditions. All right, so save DB, and let's go down here to solution and define loads. We're going to apply thermal loads, temperature on nodes. All right, so we got node 1 is a fixed temperature, so middle click. And there's a fixed temperature there. So we'll click on temperature, it's a constant value, and right there it's 200 degrees C. And we'll click OK. All right. And we'll come back here again, thermal temperature on nodes. And now we're going to come over here because it's a fixed temperature for the air temperature. And make sure we're at node 5. Click OK. And OK here. And at node 5, we had a constant temperature of 30. So click OK. And save DB. And we're ready to solve. All right, we got boundary conditions on both sides. And come down here and solve current LS. We'll click OK. Check related, produce one warning. Should the solve command be executed? Let's go see what that warning is all about. So if we go, this is the second window opened by ANSYS. So it says the program shows an initial temperature time step. Initial time step load factor is arbitrary. This is for the user to supply a suitable initial time step. So we can ignore this in this case. This is a steady state analysis, so we're not worried about any transient stuff. So we'll just go ahead and go ahead and do the solve command. So this is done. Great. And close that. Coming down here to General Postproc and list results, and we'll just look here at nodal solution. Degrees of freedom, and we got the temperatures are only degree of freedom. And look at the results there. And we got our 200 fixed and our 30 fixed, and then we see the values of the temperatures in between there. All right, that looks pretty good. So, but as always, we want to verify results. So let's look and see if these values here are legit. So I'm going to go back to the presentation and do a little analysis on what we have here. So let me get back here to the PowerPoint. So we could do this analysis. Basically, there's a temperature, fixed temperature, right, at 200 degrees here, 200 degrees C. And you can do a resistance here. Right? They can actually act like little resistors, and then you have a resistor for this material, and then a little resistor for this material. And then we'd have another resistor for the convection that happens between node 4 and node 5. And at 5, we have a fixed temperature of 30 degrees C. So between all these resistances, these different materials, different modes of heat transfer, there's a constant Q dot. So just like with an electrical circuit, there would be constant current through all these. There's a constant heat transfer rate through all these heat transfer modes, different resistances of either material or via the convection. So let's see if this Q dot holds true, that it's constant for all our cases. It's kind of our check here. All right, so if we start off with the Q dot between nodes 1 and 2, all right, that's conduction. So we got a K, A, and then we got our delta T, which we solve for, or the different T's, the different nodes, divided by L, the length of that element. All right, so let's see what we come up with. So for K, it's 0.08 watts per meter K. And we got area, we said, was 1 meter squared. And the delta T is the 200 degrees C, that was the boundary condition, minus what we solved for was that 162.3 degrees C. All that divided by the length, which was 0.05 meters. All right. So if we solve that guy out, we're going to get 60 watts. All right. So the question is, do we get 60 watts between our other two nodes? So let's go to the other end and look at convection. So if we look at Q dot between nodes 4 and 5, that's convection. So we got HA, and we got our delta T. So we got T4 minus T5. And the H is, that was, make sure I get that right, I think it was 40. Yeah, 40. So we got 40 watts per meter squared K. Area, again, is 1 meter squared. Temperature at node 4 was what we saw for, 31.5 degrees C minus the 30 degrees C fixed for the fluid temperature. And hopefully you're going to see there I got the 40 times 31.5 minus 30, we get 1.5, and that's going to give us 60 watts. All right, so those guys being the same, we can be pretty confident the rest of the results are going to be good. Probably want to check those as well, but that's one way you can verify your results, at least of the thermal analysis. All right, so let's move on to a fluid mechanics example, right, to see the generalness of the stuff we just developed. Right. So we're looking at this fluid mechanics example using, again, linear elements. So we have laminar flow in a channel. It's Poisson's flow, so we have a pressure-driven flow. So you have an overall velocity profile, which actually looks kind of messed up. Probably shouldn't be like that. We got a height h between the two plates, and we have a width w in the z direction out of the screen. All right, so starting with the governing differential equation. All right, so we have some viscous effects, and we'll have the pressure gradient, which is driving the flow, which is helping the flow move. All that equal to 0. All right, so we got the velocity of the fluid is u, dynamic viscosity is mu, the pressure drop drives the flow, and the temperature on the channel surfaces in the fluid. Actually, we don't need that. It doesn't apply to the situation. Cross that off. So boundary conditions. So we got 2 for linear elements. So we have the velocity is 0, so no slip conditions at the bottom at y equals 0. And we have no slip at the top at y equal to h. So that looks good. So note that the governing equation is the same general form as the equation we dealt for heat transfer. All right, so we had our second derivative of the psi with respect to x times the coefficient plus the second coefficient times psi plus third coefficient. All right, so in our case, psi is equal to u. All right, so we have the velocity. X is equal to y because we're changing in the y direction between the two plates. C1 is our mu, viscosity. C2, we actually don't have that term at all, it's 0. And then C3 is our pressure gradient, that's constant. All right, so the derivation we did for heat transfer, so we have the stiffness element, stiffness matrix for an element, and then we have the stiffness matrix for C1 and the stiffness for C2. All right, so for C1, all right, it's going to be our mu value. We're going to substitute in there. And for C2, we said C2 is 0. We actually don't have this term, so that term just goes away. All right, so the stiffness matrix that we have here is the viscosity over the length of our element and multiplied times our stiffness matrix that's been developed there. All right, so that's our flow resistance matrix. All right, so this was kind of its conductance before. In this case, it's a flow or the viscous effects here. From our force matrix, all right, forcing functions, we got C3 divided by L. C3 here is our pressure gradient, so we got the negative dP dx L over 2. And that's our flow forcing matrix. Kind of makes sense, right? The pressure gradient is what drives, what drives the flow. Right? So for fully developed laminar flow, we've talked about this in fluids, is that the dP dx is a constant. Right, so before we're going to sum our global stiffness and force matrices, and solve for the global matrix equation. Right, to get global K values, and then ultimately we can solve for, this would be probably global U's, and then work backwards to our local U values. All right, so looking at our 1D model here, so again the setup here is a nice Poisson's flow. That one's a lot more symmetric there. All right, again it's a constant pressure gradient that's driving it, breaking up into 5 nodes and 4 elements. 0, no slip at the 2 elements, nodes 1 and 5, no slip there, so velocity is already declared to be 0. All right, so this would be the setup for the model, and you could follow through using the same process we did for the heat transfer problem. All right, so if we want to get mass flow rate in the channel, get the total mass flow rate, we'd sum up the mass flow rates for each element. And to get those guys, all right, so we sum them up. We would use the velocity we'd have for each element, the width out of the page, times the density, because again, we're going for mass flow rate. And we're going to integrate that with respect to y from the node I to node j to solve for the m dot for that given element. So d is the density of the fluid, w is the channel width, and u is the element flow velocity. So with those, we could calculate then the mass flow rate, total mass flow rate, by summing up all the mass flow rates we got from each element. All right. So looking at how we substitute that in for our velocity here, we got our shape function form. Again, we're using linear elements, so it's the shape function node I times the velocity at node I plus the shape function node j times the velocity at node j. And if we substitute those in and do the integration, we come up with just the average. That kind of makes sense because we got linear elements. The average of the velocity at either end of the element times rho times the width of the page times the length. That gives us the mass flow rate. All right, so hopefully that makes sense for that calculation there. Again, always you want to verify your answers. Right, so like we did with the heat transfer case, to some degree of certainty to make sure you can get a lot of nice values. Hey, the thing runs, but do they make sense? All right, so you can see lots of books for conservation of energy in elements to do that analysis. But again, the big kicker here is you want to make sure you're verifying results. Exclamation points, which makes me happy. All right, so hopefully you guys enjoyed the presentation. Again, if you have any questions, let me know in the comments below, and I hope you enjoyed it. Thanks.